In the Arch1 model that we have just estimated, we only considered one leg. It's quite possible that longer legs are also significant. So instead of estimating an Arch-Q model, which is kind of a inconvenient to estimate, we can estimate an Gauge model, Gauge-1-1 model. And instead, the implementation of such analysis is straightforward. We still use the same command, arch, but we add one parameter there. We request one more estimate, is Gauge-1. So we have Arch1 already, we add a Gauge-1 there. That's basically a Gauge-1-1 model. If you press enter, once again, maximum likelihood estimation, it will show you the iteration. It took the software 7 iterations to reach the convergence. And here is the result. And you may notice that here we have R, that's the estimate of the mean. And we also have arch. So this is the arch effect. And this is the gauge effect. Or this is the coefficient of ET minus 1 hat square. And this is the effect of HT minus 1 hat. And that's the result corresponding to the output on slide 19 in my lecture notes. So this is how to estimate a gauge model. Next is the T-gauge model, threshold gauge model. So we would like to investigate different response to good news and bad news, or positive shocks and negative shocks. So all we need to do is just to specify T-gauge1 in this model. So we add one more element to be estimated. So press enter. It gives you the estimation, and you may notice that we have arch effect, T-arch effect, and gauge effect. And the constant is estimated over there. The output looks different with the one on my PowerPoint slide. So let me switch back to my PowerPoint and show you the difference. And bear in mind, we have a negative minus 4917 as the coefficient of T-gauge coefficient. So keep that in mind while I'm switching back to PowerPoint. So if we go back to our PowerPoint and have a look at the threshold arch model, or T-arch model, you may notice that the coefficient estimate of our T-arch element is positive. Actually, it's just the opposite. It's the same value, but it's positive. The reason is, in our analysis, we defined the dummy variable as A equals 1 for bad news. But in stata, the dummy variable is defined in the opposite way. So D equals 1 for good news. Or in other words, when the shock is positive. So in that case, you're not going to be surprised that a coefficient estimate is just the opposite. It's the same value, but the opposite sign, as we can see from our PowerPoint slide. You may also notice that the coefficient estimate of ET minus 1 square head is also different. This is because we have a dummy variable here. So without this part, the 0.263 coefficient, this value, is the response to good news, because that's when dt is equals to without the effect of negative news. If you define the dummy variable the opposite way, the coefficient of ET minus 1 square is going to be the effect of negative news. So let's go back to our stata output. So in the stata output, ET minus 1 has coefficients is 0.742. It's pretty large compared with the one on our PowerPoint slide, which is 0.263. But if you add this negative one to this coefficient, that will give you 0.263, which means that's the response for a positive news. So that basically means, okay, this is the total effect, 0.754. That's the total effect response for a negative news. But if it is positive news, this effect is going to be reduced by this much. So if you add those two together, that gives you the effect of positive news, which is exactly the same as the coefficient estimate on my PowerPoint slide when the dummy variable indicates negative news instead of positive news. So this is something that's seemingly inconsistent between those two sets of results. But if you understand the use of dummy variables, they are essentially the same. It's just the base for comparison are different. So this is a T-arch model. The next one is the Arch in mean model. So we release the assumption about the mean. We allow mean to change in a specific way. So it will change according to the volatility or the variance. So the command that we are going to use, we add this command in, is arch m in gauge, which means the mean needs to change according to the variance or the volatility. If you submit that, it gives you this result. So we have arch mean. This is the mean of the return. So the returns equation is not just a constant. It also has this one multiplied with HT. And we also have arch, T-arch, gauge elements there. Once again, this coefficient is just the opposite. It's of the same magnitude, but the sign is just opposite as the one in my PowerPoint slide. This one is different from the one in my output in the lecture notes. But if you add this one with this one, that will give you the coefficient in my PowerPoint slide. So they are the same. And this is how to perform those advanced analysis of a arch model.